Well, welcome back to some more Laplace Transforms. We're doing Chapter 7, Section 3, Translations and Partial Fractions. We are going to start with partial fractions today. So there's two rules that they introduce in this chapter. Rule number 1 is when it deals with what they call linear factors of partial fractions. So let's say we have this fraction that looks like this, and we want to find, and you can tell it has three of the same roots. S minus 5 is actually 3 roots of this fraction. So the way you have to set it up to figure out what simpler fraction it can be made up of this is that you have to write it in this fashion. Every factor of S minus 5 has its own fraction. And since there's no s squareds in the parentheses, the constants on the top, they're just constant. There's no functions of s. So then we're going to do exactly what we did before, is we're going to find the common denominators of this. And that common denominator is going to be s minus 5 to the third power. And if we do that, we get this fraction. And then what we're going to do is we're going to equate the fractions on the left-hand side of the equation to the right-hand side of the equation. And if we do that, we get the numerator. The numerators have to be equal. And so we need to do some math on the right-hand side. So we expand it out and group together all the terms that have the same power of s. And we get this algebraic expression. We're going to do the same things we did before, is we're going to look at the coefficients of each power of s and make the left-hand side's coefficients equal the right-hand side's coefficients. So in this case, we find a is 0, minus 10a plus b is 1, and the constants are equal to 5. So and then we can solve this, but we can see if a is 0, then that's going to make b equal to 1. And if b equals 1, then c has to equal 10. So now we have our constants that we're going to put in partial fractions. So we're going to plug them back in, and this is what our partial fraction should look like. And that's how you apply rule number 1. And you will have to use this for Laplace transforms, because if you do inverse Laplace transforms, they're much easier in this format. And we'll get into this more later. So rule number 2 has to deal with quadratic factors of partial fractions. So let's say you have a partial fraction that looks like this. Now you see in the parentheses in the bottom of the fraction, s is now squared. When that happens, that changes the guess of the partial fraction. So for each root here, what you're going to want to do is, since s now down here on the denominator is squared, you have to put at least one factor of s up in there. If s was cubed, you'd have to put an s squared and an s up on the top of the fraction. So we have our two fractions here. Every time if you have a power here of the denominator, the whole thing is squared. So you have to write it out twice, 1 to the first power, 1 to the second power. And just like the last one, if there's 3, you need a third term. Alright, so we're going to find a common denominator again. And once we find the common denominator, we're going to group the numerators all on the top, and we're going to set the two numerators on the left-hand side and the right-hand side to be equal. Let's do some algebra on the right-hand side. Group together all the coefficients associated with a particular power of s. So I've grouped together the s cubes, the s squares, the s's, and the constants. And again, we do the exact same thing as we've done before. We have to make the coefficients in front of the same factors of s on the right-hand side equal to the coefficients on the left-hand side. So if we do that, we find out again that a is 0, that the coefficient in front of x squared minus 4a plus b has to equal 1. The coefficients in front of the s terms, it has to equal 0. And the coefficient in front of the constants has to be 6. So now we can solve this system of equations. We have 4 equations and 4 unknowns. if we solve it, you will find that the constants equal this. Now we can take this and plug it back into our partial fractions. If we do that, we get something that looks like this. And so now we can, now we're done. We should be able to take some inverse Laplace transforms if we needed to. But this is just to show you how to handle partial fractions. And yes, we will have to use them in helping us solve our differential equation. And there's plenty more examples in the book if you need more practice. Alright, new rule for Laplace transformations. It's called the translation on the s-axis rule. We deal with a lot of functions. That's an exponential function times some other function of f. And if you want to take the Laplace transform of that, there's a special Laplace transform. And what you need to do is, in order to take this Laplace transform, you have to know what the Laplace transform of f is already. And if you do, then the Laplace transform of the exponential times f is this translation along the x-axis. So how do you read this? Well, you have to go find the Laplace transform for the function of f of t. Everywhere you see an s in the Laplace transform of f of t, you change the s to an s minus a. Okay, so let's do some examples of this. And if you have an inverse Laplace transform, you look for a function that everywhere there where s would be, you see an s minus a, you can transform it back into this equation. So let's do an example to show you what a translation is. So we're going to look at problem 1. We want to find, well, here's our function, t to the 4th power times e to the pi t. That fits the Laplace transform of a translation on the s-axis. And so we have to find f of s. In our case, f of s is t to the 4th power. We can find the Laplace transform of t to the 4th power. It is equivalent to this, 4 factorial divided by s to the 5th power. Now that we have that, we can find the Laplace transform of t to the 4th power e to the pi t. In this case, pi is equal to a. So everywhere I see an s in my Laplace transform of t to the 4th power, I replace that with s minus pi. And this gives us a Laplace transform. Alright, let's try it again. Let's look at problem 4 on this section. And here our function is e to the minus 1/2 times t times the cosine of 2 times the whole thing, t minus 8 divided, or t minus pi divided by 8. Now, to do the Laplace transform of this, what is our function? What is f of s? Is what we got to find. Now to do that, well, that's going to be the Laplace transform of this cosine term. But if you look up in the table, you're not going to find one that looks like that. So we have to do some algebra to try and simplify this. So the first thing I'm going to do is multiply through by 2, and we get this. And then I have this cosine term. But there is no Laplace transform that matches this. So what we have to do is simplify this, and we're going to use what is referred to as the subtraction of two angles of cosine. We've used this before. I don't know if we've used this in this class. Maybe, I think I have. So I'm going to apply that to my function, and we get, now we have a sine 2t, cosine 2t times some constants. And it just so happens that those constants is the square root of 2 over 2. So now I can take the Laplace transform of this version of f of t. If I do that, these are equivalent. So let's take the Laplace transform. I can distribute it across the sums, and then I can factor out the constants. Now all I have to do is take the Laplace transform of cosine of 2t and sine of 2t, and those are existing in our tables. If we do that, I get this Laplace transform. Well, if you notice, I can simplify this a little bit. It's the same denominator, so what we can do is add them together. So this would be our f of s that we need to translate on the s-axis. So I can write everywhere I see an s, I'm going to replace it with an s minus a minus 1/2. So a minus and a minus makes a plus, so it's an s plus 1/2, s plus 1/2. And this is my translation. I can simplify the algebra a little bit, and I get this is the Laplace transform for e to the minus 1/2 t times the cosine of 2t minus pi divided by 4. Alright, so that is an example of using the translation along the s-axis Laplace transform. Alright, so we're going to have to practice taking inverse Laplace transforms and using some of the new techniques we have, these partial fraction techniques, plus this translation technique to see if we can do inverse Laplace transforms. So I'm going to look at this problem. I have to do an inverse Laplace transform of this. What is that going to be? Well, there's nothing that shows up in the table that's like this. I have to simplify it by using partial fractions again. Using the same technique as earlier, I separate all the powers into a single power, a squared power, and a cubed power, and then find a common denominator. And then once again, I want to put have my common denominator, and find once I find that, I can make the two numerators on the left-hand side equal to the numerator on the right-hand side. Do some algebra on the numerator on the right-hand side, and group together all the powers with the same power of s, and I get this. And then when I have this, I can equate the coefficients in front of the particular power of s to on the left-hand side to that on the right-hand side. So if I do this, I find out that a equals 0 for s squared. The s powers give us 1 equals 2a plus b, and the constant gives us a minus 1 equals a plus b plus c. Now, if you solve this for the constants, you will find out that b is 1, and c has to be a minus 2. And so now I can take those constants and plug them back into my partial fraction determination. And so now I have an equivalent representation of fractions, and I can take the inverse Laplace transform of this function now. So let's do that. These two are equivalent. I want to do the one on the right because it shows up in the table of values for Laplace transforms. If I do that, I can distribute the inverse Laplace transform to each one, and then what I can do is factor out the constants. So, and at this particular rate, I can look up the Laplace transform here. This is going to be a translation in x where a is equal to -1 in both cases. So if I do the inverse Laplace transform for this, I should get a minus e to the minus t times t minus 2e to the minus t times t squared. And then you could factor out the e to the minus t if you wanted to. And you've done your inverse Laplace transform. Okay, so again, why would you want to do this? Well, the whole reason for Laplace transforms is it transforms a differential equation into a algebraic equation. Instead of doing calculus, you do algebra. Although it ends up being a lot of algebra. Alright, so let's find the Laplace transform of this, problem 14. So here we have a little bit different function in the denominator, and so I'm going to factor it out in s. It's pretty easy to do. What you want to do is find the roots in the denominator, and you can now I can simplify or factor the roots for the s squared minus s minus 2, and if you do that, you find out the roots are s, s minus 2, and s plus 1. And then again, you can write out a partial fraction that looks like this, and then you need to find the common denominator again. And if we do that, if you find the common denominator, then the numerator on the left is equal to the numerator on the right. And if we do this, I find this for my numerator, and then once I get my numerator, I can do some algebra to expand out the powers of s's, and then you group the power. Every term that has the same power s, you group them together. And now once we've done that, we can the coefficients on the left-hand side have to equal the coefficients on the right-hand side for the same power in s. So for s squared, the left-hand side is 0, the right-hand side is a plus b plus c. For s, the left-hand side is 5, the right-hand side is minus a minus 2c plus b, and for the constants, the left-hand side is minus 4, and the right-hand side is minus 2a. And then we can solve this. If we solve for those coefficients, you will find out that a equals 2, b equals 1, and c equals minus 3. And then we can plug them back into our representation of the partial fractions. And now I can take the Laplace transform of this, because the Laplace transform on the right-hand side here shows up in our table of Laplace transforms. And if you do the Laplace transform of the inverse Laplace transform of this, you get 2t plus e to the 2t times t minus 3e to the minus t times t. And you've done your inverse Laplace transform using methods of partial fractions and the translation of on the x-axis of Laplace transforms. Well, how would you use these Laplace transforms to solve a differential equation? Well, let's do one. So we're looking at problem 34. Problem 34 is this. It's a fourth order differential equation. It's a homogeneous differential equation. It has constant coefficients, and we have the initial conditions for this differential equation. So what we need to do is take the Laplace transform of our entire equation. You will end up with this. And then you have to do the Laplace transform of each into one. So the Laplace transform of the fourth order derivative is right here, plus 13 times the Laplace transform of the second order derivative, plus 36 times the Laplace transform of x, which is just capital X of s in this case. So now what do? Well, we're going to evaluate our initial conditions. We know that at the position at t equals 0 of x is 0. The second derivative at x, the second derivative of x at t equals 0 is 0. We know the first derivative of x at t equals 0 is minus 2, and we know the third derivative of x at t equals 0 is minus 13. So we plug them all in, and we come up with this expression after we're done. Now we just need to group all the capital X's together and everything else that doesn't have an X into it. If we do that, we get this expression. Now I need to solve for capital X. I solve for capital X, and this is my Laplace transform of my differential equation. Now to find x of t, I have to take the inverse of this. I'll take the inverse Laplace transform of this. The problem is this function will not show up in your tables. We have to simplify it to do that. So what you need to do is calculate the roots of the denominator. If we do that, you will find out that it is s squared plus 4 times s squared plus 9. Now I can create a partial fraction for this. You notice that the s's are squared in my denominator, so that requires me to put a factor of s in my prediction for the numerators of each fraction. Now I need to make the left-hand side equal to the right-hand side. To do that, I find my common denominator. I find my common denominator, and I can set these two fractions equal. And now I have my numerator equal to, on the left-hand side, equal to the numerator on the right-hand side. Now I just have to do some algebra to expand the numerator on the right. Okay, let's continue this. We have the numerator from the left-hand side should equal the numerator of the right-hand side. And then if you expand the numerator on the right-hand side and group by powers of s, you get this. And again, we set the coefficients of each power of s equal to, on the left-hand side, equal to whatever the coefficient is on the right-hand side, and you get 4 equations and 4 unknowns. And if you solve those 4 equations and 4 unknowns, you will find out that a equals 0, c equals 0, b equals 31 over 3, and minus 37 over 3 equals d. And then I can plug that back into my representation of the partial fractions used to describe the function of capital X. And now I can take the inverse Laplace transform. Now, when you do that, to make the functions represent what they are in the tables, the s squared plus 4 is a sine inverse. It's a Laplace transform with sine of 2t, but it needs to have a 2 on top. So I have included my 2 for the s squared plus 4 there, and then for the s squared plus 9, you have to have a 3 on top, and I've included my 3. Once you do that, you can do the complete transformation, and you find out that the solution for this differential equation is 31 divided by 6 sine of 2t minus 37 divided by 9 sine of 3t. And you are done with that